Okay, next up in the further maths chapter summaries is differential equations, which is Core Pure Year 2, Chapter 7. I think they call it methods in differential equations. But really what this chapter does is just focuses on the skills that are required to be able to solve first order and second order differential equations. Probably one of my favourite chapters. In the next chapter summary, the last one, Chapter 8, we will be looking at the modelling kind of context. So expect this to be very, very skills based here. And as I always say in these videos, it is not possible for the chapter summaries to cover all the ways examiners can assess the topic. In particular, this one is going to be very skills. So we're going to start with ways that you could two examples of first order differential equations. And of course, there are actually kind of three ways that you could solve a first order differential equation in A-level maths and further maths. The first one is to separate the variables. That's the kind of standard one that we have from A-level maths. Tech is used is you may need y to, and you will multiply this thing by the integrating factor, and the integrating factor. What this then does is it forces the equation into a reverse product rule form. So we have two questions here. And the reason I've written them in this order of three things here is the first thing you should always check for. It would be very, very rare for it to happen, but it could be a separate the variables. Then you should check if it's ready for a reverse product rule, and then you should do the integrating factor. So when we look at this first one here, actually, I don't know if you can spot this, but this is already in the reverse product rule form that we have. If you did divide by x squared, divide by x squared, and divide by x squared, so that you got it into this form here, and then you did the integrating factor, you would squared, divide, and spot this, but this is divide by x squared, so that you got it into this form here, and then you do the integrating factor, you would find the integrating factor is x squared, so that when you multiply it back through, you come to this form that we have here. So the reverse product rule form is really saying this thing is the result of a differentiation of a product. And I'm wondering if you know what that product is going to be. The product is going to be, kind of like looking at this first part here, it is the derivative with respect to x of x squared y. And you know when you differentiate x squared y, you would get x squared dy dx, that's keeping this and differentiating this, and then you would differentiate this to get the 2x and you would keep the y. So this part on the left-hand side is the result of this differentiation. And that is therefore equal to 1 over x squared, which is x to the power of minus 2. So this is what we mean by the reverse product rule. We've spotted that this is the result of a product rule differentiation. We are now going to get rid of this sort of differentiation part by doing the opposite, which is to integrate, which means that x squared y must be the integral of x to the power of minus 2 with respect to x. So we have that x squared y is equal to, I'm going to increase the power and divide by that new power plus c. So we have x for product 1 over x squared, which is x to the power of minus 2. So this is what we mean by the reverse product rule. We've spotted that this is the result of a product rule differentiation. We are now going to get rid of this sort of differentiation part by doing the opposite, which is to integrate, which means that x squared y must be the integral of x to the power of minus 2 with respect to x. So we have that x squared y is equal to, I'm going to increase the power and divide by that new power plus c. So we have x squared y equals minus 1 over x plus, and divide by doing the opposite, which is to integrate, which means that x squared y must be the integral of x to the power of minus 2 with respect to x. So we have that x squared y is equal to, is x to the power of minus 2. So this is what we mean by this differentiation. And that is therefore equal to 1 over x squared, which is x to the power of minus 2. So this is what we mean by the reverse product rule we've spotted, which we have that x squared y is equal to, I'm going to increase the power and divide by that new power plus c. So we have x squared y equals minus 1 over x plus c, and can substitute straight into this. So if y is 0, equals minus 1 over x is 0, so we can substitute straight into this. So if y is 0, we just get 0 over here, and if x is 1, we get minus 1 plus c, which means that c is equal to 1. 0 solution. So they've told us that x is 1 over x minus differentiation side is the result of this differentiation. And that is therefore equal to 1 over x squared, so the differential squared, multiplied by this y expression, and you would find that it does give you 1 over x squared. So this one was the reverse product rule. This is pretty obvious. We're going to need to use an integrating factor. It is not currently in a reverse product rule form we've got here. And we're just going to do the general solution in the form y equals f of x for this one. So we talked about this before. It needs to have dy by dx completely by itself. We've already got this function of x on the right-hand side, so I don't need to worry about that. The way I'm going to get this dy by dx by itself, so I'm just going to divide everything by tan 2x. So when I divide by tan 2x, I would have a 2 cot 2x y. So when you divide by tan, you get cot. And when I divide by tan 2x here, I just get 2. So this was, I'll write it down over here, this is dividing by tan 2x. Now what I'm going to do is use the integrating factor. So in this particular case, our p of x that we have is 2 cot 2x. So I'm going to do e to the integral of p of x with respect to x. If you want to, you can do x. So I'm going to do e to the integral of p of x with respect to x. If you want to, you can integrate this somewhere else on the page. I mean, this by itself, y rule for x completely by itself. We've already got this function of x on the right-hand side, so I don't need to worry about that. The way I'm going to get this dy by dx by itself, so I'm just going to divide everything by tan 2x. So when I divide by tan 2x, I would have a 2 cot 2x y. So when you divide by tan, you get cot. And when I divide by tan 2x here, I just get 2. So this was, I'll write it down over here, this is dividing by tan 2x. Now what I'm going to do is use the integrating factor. So in this particular case, our p of x that we have is 2 cot 2x. So I'm going to do e to the integral of p of x with respect to x. If you want to, you can integrate this somewhere else on the page, but I'm just going to do it right here. So x is dividing by tan 2x. Now what I'm going to do is use the integrating factor. So in this particular case, our p of x that we have is 2 cot 2x. So I'm going to do e in a case. Our p of x that we have is 2 cot 2x. So I'm going to do e to the integral of p of x with respect to x. If you want to, you can integrate this somewhere else on the page, but I'm just going to do it right here. So it's going to be e to the integral of 2 cot 2x dx. And I don't know if you spotted this kx to be ln of sine kx. The ln since it works is 2 with this 1 over k thing that we would have had. The ln of factor, sometimes I use the if to represent that. So I'm now going to take the equation that's here. So this is the integrating factor. Sometimes I use the if to represent that. So I'm now going to take the equation that's here and I'll multiply it all by sine 2x so that we have sine 2. x dy by dx plus 2 cot 2x y. So I'm just going to write cot 2x down as how it was originally. So we just get that it is sine 2x. So this is the integrating factor. Sometimes I use the if to represent that. So I'm now going to take the equation that's here and I'll multiply it all by sine 2x so that we have sine 2x dy by dx plus 9 I would have a 2 you spotted sine 2x, the sine 2x thing we get is was to the initial condition. I get y equals minus cot over k. It might look a bit weird if I had 6, and then we still have the minus cot 2x as well. So the only reason I used k here as my constant is it might look a bit weird if I had c cosec 2x, just two c's next to each other looked a bit strange. But if you did use it, you wouldn't be punished for that as well. So there's our general solution. C cosec 2x, just two c's next to each other looked a bit strange. But if you did use it, you wouldn't be punished for that as well. So there's our general solution written in this form. Okay, now we're going to get on to the second order homogeneous equations that we've got here. So when general solution written in this form. Okay. Now we're going to get onto the second order homogeneous equations that we've got here. So when you have any of these things, which are second order, because they've got something to a second derivative, when we have, it's literally just squared is minus 4, so a constant and cos plus b and I like stuff on the right hand side. So when you have a non-homogeneous second order differential equation where you have the same thing on the left hand side, but the f of x add 2x, well, for the x from before quicker, and plus b
So when analytical methods fail, we need to go back and use numerical methods. So we've seen that with numerical integration, so using the trapezium rule, the mid-ordinate rule, Simpson's rule, etc. Or we've also seen it with just solving equations. If you've got to that point in A-level maths where you're doing the x equals g of x method or the Newton-Raphson method, for example, they're kind of our fallback positions to be able to solve equations. If we're solving differential equations, then we've looked at some very particular formats for that allowed it to work. Whereas if you go in, so the cases that we looked at were linear differential equations, first order and second order. However, if you go into nonlinear, then finding nice solutions becomes a lot harder. And that's where we've got to start to rely on numerical methods in order to be able to have that we could work plus cubed. So the methods that we have tried to employ before, we can't anymore. And that causes a problem. So how do we go about this? Well, one way is to use Euler's step-by-step method. Now, depending on the differential equation that you get, whether formula to... So the idea is that a point that has a then we could have a point that's very close to it, this point here, so this would be x1 and this would be y1, and this distance is our step length, which we'll call h. So it's looking very similar to what I would do if we were doing trapezium rule, mid-ordinate rule, etc. Okay, so very similar to that at this point. Now the idea is that if I know a point on the curve, and that would be given by one of my initial conditions, or boundary condition for the differential equation. If I know that point, then maybe I can get to this point using a straight line. If it's close enough, I could approximate this using a straight line. Okay, that is what Euler's step-by-step method is going to try to do. Okay, and that's going to allow us to estimate that next point, or approximate that next point on the curve. So the gradient would be the difference in the y coordinates, y1 take away y0, divided by the difference in the x coordinates, which is just h. Now, as that is the gradient of the line between those 2 points, I know what the gradient of the function is, because if I use the dy by dx equals some function of x and y, then this is telling me that the gradient function is f of x comma y. So the gradient of that line can be written as f of x0, y0, where this is the gradient of the curve at the point x0, y0, at that point there. Multiplying through by h and adding y0 to both sides, I can write y1 is equal to y0 plus h times f of x0, y0. And so here, I can get the next coordinate up. And of course, this is all dependent on how close h is, how small h is. That will give a better approximation. And of course, making sure that the curve is reasonably smooth as well will allow that to work. Now, if we want to generalize this, then what I'm saying here is that then I could work out the next point along. So this point, by saying, well, y2 should be equal to y1 plus h lots of f of x1, y1. Okay? And I could keep on going over and over and over again. So this is where the formula comes from, and it's in the AQA formula booklet. So for this, we've got yr plus 1 is equal to yr plus h f of xr yr, okay, where we can get the next step so that r plus 1 is your xi, your previous one, plus h. So all that's saying is that to get x1, I need to do x0 plus h. And to get x2, I need to do x1 plus h. So we've done it for the f of xy's, right? It's exactly the same derivation for this one as well. Now, just to make it clear that it's a different looking formula, the formula booklet uses n, so yn plus 1, but that's fine, it doesn't matter. Is yn plus h times f of xn, where xn plus 1, the next x term, is xn plus h. Okay? So this is Euler's step-by-step method, and I'm going to show you an example of using it in the next video. X is equal to log base 10 of x, and the condition that y of 2 is equal to 3. So what that means is that when x is 2, y is 3. Use Euler's step-by-step method with a step length of 0.2 to obtain an estimate of the value of y of 2.4. So we want to find y when x is 2.4. Give your answer to 3 decimal places. Now the first thing is that we have dy by dx is equal to some function of x, not some function of x and y. So we're just looking at the top half here. That's what we're going to be working with. Now, notation-wise, we need to understand that what we have here is we've been given x0 and y0. So essentially, x0 is 2, and the y0 is 3. Okay, that's what that's telling us. We want to find y1. So we use our formula here. The next term in the sequence is the previous term, so y0, plus h, which is 0.2, times by f of x0. So that's f of 2. So y0 is 3. F of 2, now I need to substitute 2 into here. So that is log base 10 of 2. So log base 10 of 2 is 0.301029997. So I'm multiplying that by 0.2 and adding 3, and we get 3.060205999. Okay, so that is y1. Now, I need to get to y2, but in order to get to y2, I'm going to need x1. Okay, so I need my next x value. Now, the next x value is the previous x value plus h. So that would be x0 plus the step length, 0.2. So x0 was 2. So we should have in this video, I'm going to go through decimal places. So that is the value of y of 1, which is my y4.